Hello everyone, and today we're going to be talking about Kalman filters. So a Kalman filter is a really common filter used in state estimation, but before we get into that, we're going to motivate the problem. So this course probably looks pretty familiar to you. This is the course that your robot has been driving on for the entire RoboJackets training curriculum. And what you've done is you've been able to detect these red blobs, and you're doing other things, but this week what we're going to focus on is we're going to be trying to track mineral deposits. So the way that's going to work is that your robot will be here, something like that, and that is going to see this fiducial marker here. And then we're going to keep driving. So as we drive our robot around, we're going to progressively get more and more detections of this fiducial marker. Every time we get a detection of the fiducial marker, our code in the background is going to give you a location of that mineral deposit relative to that fiducial marker. So what you're actually going to be getting are a bunch of readings that look something like this, and they'll all be centered around this point. Now, the actual location of the mineral deposit will depend on the fiducial marker, so you'll probably have a couple for this project. So you could have a collection of them, and they're not always going to be to the right side. It's going to kind of vary where it's going to end up. Now, what we need to do is figure out where the mineral deposit is, and you need to park in that exact location. So this is really nice and all, but there's going to be a lot of noise, remember. So we need to use some algorithm to decrease that noise and estimate where that position is going to be. And we're going to use a Kalman filter for this. And the reason for that is that it's going to work better than a particle filter for this application. So if you remember from week 3 when we talked about particle filters are nice because they can predict an arbitrary probability distribution. And this is really convenient because if we don't know what our probability distribution is going to be, it makes sense to use a particle filter because we're not locked into any representation. But this week, I know exactly what our noise characteristics are. I know what the noise you're going to see is, and it's going to be Gaussian. So since it's Gaussian and we know something about the noise, we can incorporate that as part of our problem structure, and by doing so we can get a better solution than we can with a particle filter. So the nice thing about Kalman filters is, unlike particle filters that use randomly sampled particles, the Kalman filters have explicit equations for updating the distribution. So we're going to have some Gaussian distribution, which is characterized by a mean and a variance. And what we're going to do is we're going to have equations that explicitly update that mean and variance based on our sensor readings. Since we're using explicit equations, these are going to be really fast to compute, unlike a particle filter, which is rather slow because you have to go through all of the particles. Here we just have to solve a couple matrix multiplications. So to start off with, you'll have sensor models and motion up models like we had earlier with the particle filter. So remember we had that z of t is equal to some h of x of t plus some noise. We're going to have the exact same thing here, but now it's going to be represented by a matrix multiplication. This H matrix is going to do the exact same thing as this function we talked about earlier, which is take a state to an expected measurement reading, but we're going to assume some linearity of this process. And the exact same thing holds for the motion update. Before we had something where these two were concatenated into a single potentially nonlinear function, f, so we had x of t minus 1 and u of t minus 1, and then w of t minus 1. This is the same thing, but now we're explicitly saying that the dynamics are linear. There are nonlinear generalizations of the particle filter, but we will not be talking about that in this week. So now that we have the sensor model in our motion update, which is the mapping from a state to a sensor reading, as well as a state to the next state based on some control, we can use this to run our Kalman filter. Now, before I show the next slide, I'm going to show you all the equations for the Kalman filter. This is what we're going to derive by the end of the day. And the reason I'm pausing here is because I just want to mention that what we're covering now is more at a graduate level. I'm not holding any math back from you. There's a couple derivations that I kind of cheekily get around, but I am showing you the graduate level work here. This is because the work your team needs to do is more in line with what a graduate student would be capable of doing rather than an undergrad. And my goal is to bridge the gap. So if I scroll down to these equations, what I'm expecting a lot of responses is your eyes completely glaze over. You look at this equation and it's so complicated you'll never be able to figure it out. And the point I want to make is that you can figure this out. It's not that difficult. As we walk through the derivation, you'll see that it's a lot of really simple steps. And it's just looking at a giant equation initially gets very terrifying. This happens to me all the time when I look at papers. And the point I want to make to you guys today is that that's okay, but take it step by step and you'll see that pretty much anything you can figure out. So these are the equations for a Kalman filter, and this should make no sense. And we're going to get there. So who uses Kalman filters? Essentially everyone. So Kalman filters were used by NASA actually for the moon landing. So if you actually listen to the recordings, you can hear Buzz Aldrin calling out Kalman filter estimates as the lunar lander was being landed. So this is an algorithm that is key to how a lot of space applications, so it's used at NASA, JPL. I have people that I know that work there that use it all the time. And it's also used on all of our RoboJackets software teams. RoboCup uses it for their ball filter, IGBC uses it for state estimation, and RoboRacing also uses it for state estimation. This is a very fundamental algorithm that's used all the time. And it's used in a lot of research papers. So in this lecture, what we're going to do is cover some of the following topics. So we already talked about the high-level idea of what a Kalman filter is and why we could want to use it. The next thing we're going to do is derive this thing called least squared estimation, and this is the estimation algorithm that backs the Kalman filter. Then we're going to talk about how you can propagate your state and covariance, and finally we're going to derive the Kalman filter itself.